slide. Okay. Thank you very much. So yeah, so I'm going to talk about the bioinspired optical compass for purposes. I have to say that I'm not an expert in education for robots because I'm a CNRS researcher in France, which means that I'm fully dedicated for research, but I give maybe 40 hours for teaching to master students per year. And just the idea was to share with you and the community what we developed for master students and about bio-inspired design, because we are very involved in this bio-inspired sensors and our robots. We have been working on bio-inspired optical sensor inspired by the fly or bees since a long time now. So just would like to share with you our development about this bio-inspired approach. And first of all, next slide, please, Richard. Let me tell you a story about magnetic motion, which means that there is I would like to tell you a story about navigation and ant. And we know that there is a drift, for example, in the magnetic North Pole, which means that the magnetic North Pole is drifting. It's traveling from between Canada and now is heading toward Norway. And which means that the model for navigating on the Earth's surface is always updated. And because you need to update your model, and because you need to take into account this drift between the magnetic north and the true north of the Earth. And next, please. Yeah, we know that there is a problem with the GPS signal, which is not always available because you have problem with the urban canyon, for example, or the signal can be also very disturbed by leaves in the forest, for example, also. So that's that's a problem when you want to navigate without GPS now. But we know that there are solutions developed by nature and developed, for example, by this extraordinary animal, which is the Cataglyphis fortis ant. And just would like to tell you about the journey of this animal who is living in the next place and in a salt desert, in the salt flats. And you can see here this small black dot, and which is a nest of the ant, and the ant can travel. And next, please, can travel in this desert, okay, and can have this kind of trajectories. And this animal cannot use the ant cannot use pheromones because it's too hot. They travel during day at noon, where the temperature is very high. So they cannot use pheromones, but they can find somewhere a grilled animal. Next, please. And yeah, it's a grilled fly here, and they can take this fly and go back. Next, please, to the nest directly like that. This is a red trajectory here, and you can see what was the surprise of the researcher when they discovered this behavior, because it means that the ant has a kind of maybe a map or not, or also they can use something, a strategy, navigation strategy that can be used by the ant to go back straight to the nest. They can do homing in terms of robotic terminology, or they can also do dead reckoning also, which is the same thing. So next, please, Richard. So they can. This Cataglyphis ant can do path integration, which means that next they can use an odometer to measure distance, and we know that from biologists, and especially from the group of Rüdiger Wenner from the University of Zurich. They can use an odometer, so which means that they can measure the distance traveled by counting the steps, for example, or by measuring the optic flow, so which means the movement of the ground when they are walking. Okay, and they can integrate this speed measurement to estimate the distance. But they can also, next, Richard, please. Yeah, they can also they need to do that, to do this path integration, they also need to measure the heading. Okay, so at this point, you can say that we are very far from conference on educational robotics, and that we are not really so far, because this is the point I would like to talk now. It's about how to implement this ant-inspired compass. Because we know that the ant has a compass, but it's not a magnetic compass, actually. It's an optical compass, because they can measure their heading with respect to the sky and not to the magnetic north. And that's the trick used by the ant and by this Cataglyphis ant. So next, Richard, please. Yeah. Okay, so in terms of engineering curriculum, so the main objective of this course is to talk about bioinspired approach for designing optical sensor. I have 15 hours for that. And after that, the students will develop, and they will start by simulating the algorithm and the strategy used by the ant, so the strategy used to implement an optical compass. So first of all, there will be a first step in terms of development of a simulator. And after that, which is very important for us and for the student, is to confront their algorithm, the simulation with real data and real signals, okay? And they will also, we will also use a 3D CAD software for just designing very simple mechanical support for the filters, as we will see later. And after that, students will analyze their data and compare with the simulation, the results. And next, please, Richard. Okay, so what is this polarized light that you can observe in the sky? If you want to observe it, you need to use a polarized filter, because the human eye is not sensitive to the polarized light of the sky. And if you do that, next, Richard, please. If you do that, so if you see the sky through a linear polarization filter that you can buy everywhere, it's very, very simple to buy this filter. So you can find a sheet of plastic sheet of a linear polarization filter. You can see this kind of darker area in the sky, which is perpendicular to the orientation of your optical filter, given here by this dotted yellow line. And on the left side, you have the sun, okay? And along this line, you are along what we call the sun meridian, okay? So it means that by, next, you can also see that this darker area, you can see through the clouds, this area also. So it means that by looking through this filter, you can have a way to measure maybe your orientation. And the next, please, Richard. By if you do this rosace composed of this flower, kind of flower composed of this linear polarization filter that you cut out of from a sheet of polarized filter, okay? And you do this rosace, and you can see that if you see this video, maybe it should launch a video. No, maybe if you could go back. Not sure. Is there a video here or not? No, it's not included. Maybe. So okay, no, doesn't matter. So if you rotate this rosace, okay, by hand, you will see that you can observe that the darker part of this rosace, okay, is moving with the rosace. So it's always in the same direction, okay, even if you rotate the rosace, okay. And so it means that by looking at the distribution of the intensity around this rosace, okay, you can be able to measure your orientation with respect to a kind of reference existing in the sky. That's the first experiment you can do with students to try to understand what is this polarized light in the sky. And the next, please. Okay, so to learn how to implement this celestial compass, you need to understand what is the physics under. And we know that from we know that from the Rayleigh diffusion that the light coming from the sun is not polarized, but when the light enters in the atmosphere, it comes out with a polarization. It's an interaction of the light, of the sunlight with molecules in the atmosphere. And so, next, please. Yeah. So you have the sun. So the sun, the light coming from the sun is not polarized, but if when the light enters in the atmosphere, thank you, Richard. So it's like the sunlight passes through polarizer, which is polarized filter. And so at the output of the atmosphere, the light is partially or fully or not polarized. It depends on how you observe this light in the sky. And by using what is called an analyzer, which is another polarized filter and a photodiode, okay. And if you rotate this analyzer with respect to the sky, as we did with the rosas, for example, with the flower, you can measure this. Next, please. This Malus law. Sorry, could you go back? We should no. There is no. And if you do next, if you push, no, doesn't work. Doesn't matter if it doesn't happen. No. We should see a sinusoidal variation. No, curve, no. I cannot see it, but. So, no. Okay. So we can measure this Malus law, which is basically a sinusoidal variation depending on the angular orientation of the filter. So we developed this quite simple device setup to try to reproduce this measurement of the angular orientation of a sensor with respect to the polarized light of the sky. So we use a blue LED to emulate the light coming from the sky, and we place just a polarized filter at the output of the LED. And this blue polarized lighting is lighting a sensor placed on a rotating table that you can rotate by hand. And all these parts can be designed and realized by using a laser cut machine. So it's very easy to do that. It's made of plastic and so you can place your sensor on this rotating plate, okay? And the sensor is basically a photodiode and a polarized filter, which is the analyzer. So you can measure the Malus law by rotating the sensor, okay, with respect to the blue LED. And next, please. Yeah. So this is the celestial compass we developed with a master of students. It's composed of off-the-shelf components for implementing the compass. We have an Arduino Leonardo board and light sensor, which comes from the Groove company. And also the support, the wooden support can be designed by, can be made by using a laser cut machine. You can find polarized filter. It's commercial very, very easily. And we just developed, by using a 3D printer, the mechanical support of the polarized filter, so between the filter and the photodiode. And next, please, yeah. Yeah, this is the part we designed with the students, just a simple part to put the polarized filter at the right place over the photodiode. Okay, next, please. So several points are explored by master students here. So they can learn how to use a nonlinear least mean square method to calibrate their sensor. They can write how to write quite simple simulator on their MATLAB by using the physics we know about the Malus law, for example. and they can use the modeling, the Rayleigh diffusion to do that. And so it's in French here, but they can also do the signal acquisition with Arduino and estimate the data and analyze the data. Please, next, please. So there are two main papers that I give to the students. And from these two papers, they have to read them, and there are two different approaches they can choose to estimate the heading. So the first approach is to use two pairs of orthogonal filters placed over photodiodes. So this is the first approach on the left side. And the second approach is to use a distribution, an angular distribution of polarized filter, okay? And as they know the angle between each filter, here on the right side, they can just use very easily least mean square method, because you measure the same thing, the same parameter with a set of data, or 4 output data. You measure the same thing, which is the malus law, so you can, it's a very, very efficient or I would say emblematic example of using the least mean square in this case. Okay, so the next, please. So this is what they have to measure or simulate. This is the malus law for each photodiode. This malus law is the cosinus of the angle orientation of the sensor, which we are looking for. They have to estimate this angle, which is here the angle phi, and they know the angular distribution of the sensor, and they also have to calibrate the gain of each sensor. And to do that, they have to, as you will see later, they have to do curve fitting and calibrate the sensor. It means that they have to find the gain, which is different from each photosensor, because each photodiode, they don't have the same sensitivity, so they have a different gain, so they have to calibrate and find this gain. Okay, so yeah, so let's start with this distribution of the photosensor, and they rotate this sensor by a certain angle, okay? And the next, please. And with the simulation, so they implement the malus law for each photodiode, and they can also add noise, and they obtain these 4 signals, okay? And you can see that these signals have different amplitude, okay? It's due to the gain, the difference in the gain from each photodiode. And from these simulated noisy signals, they can do curve fitting, next please, and by using nonlinear least mean square method, because we know that what we are looking for the malus law. We know exactly the model, so you can apply this method here to do curve fitting, and that's what they did. Okay, the next please. And so by using an Arduino and a computer, and they could also do the acquisition of real signals. And I use this very, very cool term software, which is very cool, because with this cool term software, you can implement serial link between the Arduino and the computer, and do the acquisition of the signal without typing any code or C code or something. So it's very, very convenient software. And you can just put your data in the file automatically by using this cool term software. Just have to write some very, very simple C code with Arduino just to do the acquisition of the analog signals and send the value over the serial link between the Arduino and the PC and the computer. Okay, so now, yeah, we would like to switch to Python. So all the analysis and the simulation is done with MATLAB, but we would like to switch to Python because it's free, and so that we think to do that in a further development. And the next, please, yeah. So this is an example of the results they obtained. So this is acquisition of the real signals. And after that, they apply a curve fitting, and they apply so a normalization of the amplitude. Okay, so because when you identify the gain of each photodiode by using the least mean square method, you can so apply a normalization to normalize the amplitude. And after that, you can apply a method described in our paper, or just using the least mean square method, nonlinear least mean square method to estimate the heading, which is described also in our paper. So next, please, yeah, Richard. And this is an example of the heading estimation. Just could you go back to the, yeah, so this is the blue curve is the heading, the calculated heading from the real data, and which is about almost linear, as you can see. And in yellow is the degree of polarization, because for the polarized light, you have two parameters, the degree, which is the intensity of polarization, and the angle of polarization, okay? And the angle of polarization is, in our case, the heading, okay? So the orientation of the sensor with respect to the sky. And that's all, and thank you, and sorry again for this problem with my screen sharing, and thank you, Richard, and if you are interested, you can read further reading about our paper on polarized skylight and on-based navigation.